All right, good morning, everyone. Uh, we're going to continue with our notes. We talked about parent functions yesterday, so we're just going to look at some transformations. And if we know what the parent graphs look like, and if we know there's some basics about transformations, we can create a ballpark idea of the graph without feeling like we have to look at every order pair or have to use our graphing calculator to get a picture of the graph. So spend a minute there to copy down the transformations. Descriptions, and then we can look at some examples. And then we'll use the second half of class to do trig review. So given parent function f of x, the family function can be represented by the transform function. F of x equals negative a times f of x minus h plus k. So the negative, the a, the h, the k, they all do something to the parent graph. So anything that is any number that's being added or subtracted inside the expression, it could be inside the parentheses, it could be inside the radical, or inside the absolute value, whatever the parent function is, that's going to take the graph from 0, 0, and it's going to shift it either left or right. But just think opposites of what you would normally expect if something is inside the expression. So a plus h, it's going to shift the graph left, and minus h, it's going to shift the graph right. So it's going to be kind of opposite of what you normally expect. Any number that is outside the expression that's being added or subtracted, then that's going to end up shifting the graph, the parent graph, either up or down. Shifting up would be a positive number, and any number that is subtracted from the expression, it's going to shift the graph down. So that is more intuitive, right? We associate positive with going up, negative with going down, so that's still the same. It's the left and right that feels a little bit opposite. Any number that's being multiplied to the parent graph is going to end up giving us a stretch or a compress, a vertical stretch or compress. So if it's like 2 times the expression or 3 times or 4 times, that's going to end up taking the graph and it's going to kind of stretch it vertically. Compress will be like 1/2, 1/3, 1/4. The value is less than 1, it's going to end up compressing it. Sometimes I feel like I've seen students who consider the negative along with A. So they see a -4 and they feel like that's just one transformation. It's actually 2 transformations. We want to just we don't want to associate the negative with the number. So negative is something else. So negative is going to end up reflecting the graph over the x-axis. And then the number that you see there, if it's -4, then the negative is doing the transformation and the 4 is being is going to stretch the graph. The confusion that sometimes students experience is they see -4 and they say, oh, that's less than 1. That's less than 1, so therefore that must be a compression, but they're actually 2 separate transformations. Okay, let's look at number 1 here. So again, the big benefit of knowing transformations and parent graphs, it allows us to sketch the graph quickly without, I mean, it may not be super accurate, but it's enough for us to get an idea of the graph. So we know that the f of x equals 2 times x minus 3 squared plus 1. This is really coming from a quadratic function, right? This is ultimately under the category of quadratics. So we know that this the parent graph is y equals x squared. Transformation. We know that y equals x squared starts at 0, 0, and then the -3 and 1 is going to take the graph and it's going to shift it. So normally the vertex is 0, 0 for y equals x squared. But now what's my new vertex going to be? Yeah, 3, 1, right? So it's always going to be the opposite of what you see inside the parentheses or radical or absolute value. And then this one is the y value. So it's going to move to the right 1 and up 1 unit. So we're taking that center vertex and we're shifting it right and up 1. So my new vertex is now going to be 3, 1, right? It's going to just shift the graph 3, 1. And then what is the 2 going to do to it? Yeah, take the parabola and it's going to stretch it. So stretch factor of 2. So we can go to 3, 1. And normally your graph would be kind of up 1 over 1 in terms of, but I'm not really, the accuracy of your graph is not that important. It's just the idea that, okay, I know it's going to be a stretch. So I know my graph is going to be a little bit more narrow than before. And we just want to have a good enough graph where our domain and range is probably going to be still accurate. So the stretch is not going to impact your domain or your range. Okay, domain and range. Domain is still all real numbers, and then the range is now going to be what is the lowest y value that we see? 1. Yeah, so 1 to infinity. Okay, number 2, y equals negative root x plus 3 plus 1. We know that this is coming from a parent graph of y equals square root of x. And we know that y equals square root of x looks like this. It starts at 0, 0, and it's going to move up, right? So Most of your parent graphs is centered at 0, 0. Not every graph, but essentially, I think that's a pretty, let's see, all the, okay, not every one, but most of your parent graphs are, you can think of it as, okay, starting around the origin around 0, 0. This one, though, is going to take that 0, 0, and what's going to happen to that starting point? It's going to shift. What's that 3 going to do? Which direction is that plus 3 going to move? Yeah, to the left. So left 3 and up 1. So our starting point was 0, 0, but now we can say our starting point is going to be negative 3, 1. Normally the graph will go up, right? But what is this negative going to do? Reflects it over the x-axis. So imagine a sideways parabola, but now we're going to just show the other side of that sideways parabola. So instead of going up and over to the right, it's going to go down over to the right. So we're not so worried about getting all the order pairs correct. We're just trying to get the shape correct and the starting point. Okay, domain and range. Domain, we start as far left as negative 3. We're moving to the right, and then range, the lowest y value. This arrow is going to eventually make its way down to negative infinity, so it's going to go as low as negative infinity, but it's going to go as high as the starting point, which has a y value of 1. Okay, absolute value of x plus 4 minus 1. We know that this is coming from a parent graph of y equals absolute value of x. We know absolute value of x is centered at 0, 0, looks like a V. So we know that 0, 0 is going to get shifted to the left 4 and down 1. The idea is that if we can find a starting point or a vertex, if we can shift that graph to where it needs to be, then we can just kind of build our graph from that point. So my new vertex is now going to be negative 4, negative 1. It was 0, 0, but I'm shifting my vertex left 4 and down 1. No stretch, no compression, no reflection. So it's just going to be up 1 over 1. Okay, domain and range. The arrows are going left and right towards infinity and infinity, so all real numbers. But the range, we do have a lowest y value of negative 1, and it's going to go from lowest y value negative 1 to highest y value infinity. Okay, next page. Okay, this is coming from the rational function. Parent graph is y equals 1 over x. 1 over x looks like this. Vertical asymptote, horizontal asymptote. So it's basically going to take this and everything is going to be shifted in the direction that the +1 and -3 is going to do. Now you see this +1 is inside, or it's inside the expression here. So we can think of this as kind of shifting the graph left 1 unit. You can also think of it as, oh, that's my new vertical asymptote, which is at -1. And then the -3 is going to take that horizontal asymptote and it's going to shift it down 3 units. So we can think of it as just moving the asymptotes left 1 and down 3, and then we can just kind of sketch the graph around it. The 2 is going to end up stretching the graph, but we talked about how the stretching doesn't really change much in terms of the domain and range. So we can make the graph maybe slightly, we kind of stretch it a little bit to make it maybe a little steeper, but visually it's going to be tough to tell. But as long as we know what it's doing, it's not really going to affect the look of our graph. Okay. So we have a new vertical asymptote at x equals -1, and we have a new horizontal asymptote at y equals -3. So in this case, we're actually going to move the restrictions around. If we can move the restrictions around, we can kind of just create our graph around it and really don't have to worry about order pairs. So -1. We're just going to build our graph around the asymptotes. Five and six are important. Exponential functions, log functions. We're going to see quite a bit of that in our course. So we're not going to hit exponentials and logs until later in the semester, but I want to spend time. Oh, wait, I forgot about the domain and range. So let's do domain and range. So this graph extends from -infinity all the way to my asymptote, and then to the right of the asymptote. So and then for my y values, I'm going to start all the way down at -infinity, move up to the break, which is my horizontal asymptote, which is at -3, and then pick up from -3 to +infinity. Yeah, exponential functions, e to the x and natural log are important. So we're going to just go ahead and do some review now, and then we'll pick up again later in the semester. So we know that this is coming from y equals e to the x. Let me just create some order pairs for e to the x. And we just need a couple of points. And then, easy order pair is 0. If I know that anything raised to the 0 power is going to be 1, so that's an easy order pair. And then e to the 1 is just going to be e and E is around 2.7. And we know that there is a horizontal asymptote at y equals 0. All your exponential functions will have that. So, sorry, I'm not going to put it on this graph here. I'm just going to put it to the side so we can kind of have a reference point. So 0, 1, and 1 E, which is 2.7. I'm just going to just put it somewhere here. Okay, so this is how our graph normally looks, our parent graph, right? E to the x. So e to the x plus 2 minus 3 is going to end up, we can just kind of follow this point here, right? This is an easy point, 0, 1. We just take this point and we can shift it which direction? Left 2 and down 3, right? So just from that 0, 1, we'll go left 2, down 3. And also, this -3 is also going to indicate where your new horizontal asymptote is. So without any number there, you can think of it as +0. That +0 is the asymptote. So -3 is going to shift the asymptote down 3 units. So we said from 0, 1, it's going to go left 2, down 3. And if I just have 1 point, that's should be enough because I know that the asymptote will tell me where my graph is going to flatten out. And as soon as I hit that point, my graph is going to start to increase in its steepness. Okay. We just want to really ballpark graph. We're not really concerned about accuracy of order pairs here. But enough for us to build our domain and range. Domain, all real numbers. Range, the graph is never going to sit below the asymptote. So everything is above the asymptote. So from -3 to infinity. Next up, y equals natural log of x minus 3 plus 2. Let's do the parent graph first. Okay, y equals natural log of x. There's going to be a vertical asymptote. And let me just build out a couple of order pairs so we can kind of see here. Natural log of 1 is always going to be 0. Natural log of e is always going to be 1. So e is around 2.7. So we can see that we talked about how exponentials and logs are inverses of each other. So it makes sense that all these order pairs are flip-flop. There's a 0, 1 for e to the x. There must be a 1, 0 on natural log. If there's a 1, comma e on e to the x, there must be e, comma 1. So if I graph these points here, 1, 0. E is around 2.7, so just rough estimate where that 2.7 is, go up 1. So our graph will look something like this. Okay, there's a shape of your natural log graph. So again, I'm going to focus in on that 1, 0 here. Before, we would have a horizontal asymptote with exponentials. So now logs, we're going to have a vertical asymptote. So the asymptote was at 0, but now that asymptote is going to be shifted to the right 3 units. And that +2 is basically going to take my order pair. My order pair is also going to move 3 units to the right. So 3 units to the right and up 2 units. Those are 1, 0, 1, 2, 3. But it's really ultimately is not that important because our graph is going to still kind of have that same shape. we're just creating a general quick sketch of the graph without having to do all the details of order pairs. Just enough to build our domain and range. That's really what's important here. Okay, domain is everything to the right of 3. Sorry, 3 to infinity. And then your range is all real numbers. Okay, next page. So last year, you guys spent quite a bit of time on trig. So remember, you guys did trig identities. You did verifying trig identities. You guys did sum and difference, law of sines, law of cosines, all that, right? But we don't have to worry about most of trig from last year. But the one big thing that we need to know is unit circle. So we're going to review unit circle now, but we're going to pick up at the end of the semester with our trig unit. So ultimately, we're going to have to be able to memorize it. You guys have memorized it before, so hopefully, memorizing it now, and then a couple months from now, by the end of next year, you'll feel, even more comfortable. So, but let's review. With unit circle, I think everyone may have a different way of memorizing unit circle, which is fine, but I'm just going to present one way, and then we can build it out, and then we can come back to it later. So all of our order pairs are telling us about a cosine and sine values. So we're going to create all these order pairs, and all these order pairs, x is going to represent your cosine, and y is going to represent your sine. The most important quadrant is first quadrant, because if we can figure out first quadrant, then everything else is just variations of those order pairs, with maybe the signs being a little different for the ratios. Right. So unit circle means that all of my radius is 1 unit away from my center. So these are easy order pairs, right? This is exactly, if I'm moving exactly on the x and y axis, then I'm going to be exactly 1 unit away. So this order pair is 1, 0. And this order pair is 0. Pi over 3, pi over 4, pi over 6. Many different ways to memorize this. I do it this way, where I know that all of my order pairs have a 2 in the denominator. They're all going to be 2. So I'm starting to up. So everything is divided by 2. I'm starting at the upper left corner here. I'm just going to count 1, 2, 3, and then up 1, 2, 3. I'm going to put a square root over all my numerators, except 1, because square root of 1 is just 1. So I'm just going to leave that alone. So I'm going to put square root of 3, and then just put all my radicals with the numerator. Again, leaving the 1 alone. I can do square root of 1, but I can reduce square root of 1 to just be 1. So with this first quadrant, we can find cosine and sine and also all the remaining trig values. So for instance, cosine of pi over 3 is 1/2. Sine of pi over 6 is 1/2. Cosine of pi over 6 is 3 over 2. So any x value is referencing cosine. Any of the y values is referencing sine. And then let's review the other 4 trig functions here. Tangent is just y over x, or you can think of it as sine over cosine. So if I want to find the tangent of pi over 3, it'll just be root 3 over 2 over 1/2. But to make it easier for myself, I just always cover up the denominator. I know my denominators will cancel out, so it's just my numerator divided by my numerator. So root 3 over 1 will be tangent of pi over 3. Tangent of pi over 4, which is be root 2 over root 2, which is 1. Tangent of 0, which is be 0 over 1, which is 0. We know that cotangent is just the reciprocal of tangent, so it's just x over y. Secant is just 1 over x, or just the reciprocal of my cosine. So I can just take my cosine, and then if I want to find the secant of pi over 3, I can just take that related cosine ratio and just flip it. So cosine of pi over 3 is 1/2, therefore secant of pi over 3 is just going to be 2 over 1. It's 1 over 1/2, but if you just think of it as, oh, that's the reciprocal of my fraction, I can just flip the fraction rather than writing it as 1 over 1/2. And then cosecant of theta is 1 over y. It's just the reciprocal of my y value over my sine. Now, all your quadrants will share these order pairs. Just the signs are a little bit different. So I have this ASTC as a way of helping me remember which trig functions are positive, which ones are negative. So you know that everything in the first quadrant is going to be positive x, positive y. So all your trig functions will be positive in the first quadrant. Second quadrant, this S represents sine. So anything that is sine related, such as sine and cosecant, are the only ones that's positive. Everything else is going to be negative, because in the second quadrant, all your x values are negative and all your y values are positive. Tangent is going to be the only one positive in the third quadrant, because my order pair is negative, negative. And so anytime I divide negative with a negative, I'm going to get a positive. So tangent and cotangent are the only one that's positive. Everything else is going to be negative in the third quadrant. Okay. In the fourth quadrant, my x value is going to be positive. My y value is negative. So that C represents only cosine and its reciprocal is positive. Everything else is negative. A for all, S for sine, T for tangent, and C for cos. So with UniCircle, we're going to be dealing mainly with radians. We're not going to see degrees much. So I think it's more important that we know our radians around the UniCircle. So I'm just going to build them out. So we know that this is either 0 or 2 pi, depending on whether we're here or we're making our way all the way around. Next up, pi over 2. We're just moving along the quadrants here. Then pi, and then 3 pi over 2. So I think, from my previous experience, first quadrant, students don't have issues. It's the second, third, and fourth quadrant that we sometimes forget or have a little bit more trouble remembering what the radian measures are. Let me just do this here. So this is pi over 3, pi over 4, pi over 6. Okay. Now, all the measures that are closest to the x-axis will have the same denominator. So anything that's closest to the x-axis, they will all share a fractional value of 6. Anything in the middle is going to be divided by 4. Anything that's furthest away from the x-axis will be divided by 3. I'm just going to different colors here too. Color coordinate here. So I know that my second quadrant is going to be divided by 3, divided by 4, divided by 6. And my numerator is all going to be 1 unit less than my denominator. So 1 less than 3 is 2, so this is 2 pi over 3. 1 less than 4 is 3, 3 pi over 4. 1 less than 6 is 5, so 5 pi over 6. Again, closest to the x-axis is divided by 6. The middle is 4. Furthest away from the x-axis divided by 3. Now the third quadrant, all my numerator is 1 unit more than my denominator. So 1 more than 6 is 7. 1 more than 4 is 5. 1 more than 3 is 4. Right. Divided by 3, divided by 4, divided by 6. The fourth quadrant is going to be an odd number in the numerator, but it's always going to be 1 less than double the denominator. So if I double 3, I get 6. 6 minus 1 is 5. If I double 4, I get 8. 8 minus 1 is 7. If I double 6, I get 12. 12 minus 1 is 11. And also, we know it's going to be less than double because we know double is going to be 2 pi. So if we do exactly double or more than double, we know that these all should be values that's less than 2 pi. So slightly less than 6 is 5/3, slightly less than 8/4 is 7/4, slightly less than 12/6 is 11/6. Right, we can just copy all these order pairs. All the divided by 3 will have the same order pair. Just the signs will be a little different. So in the second quadrant, all your x value is negative, all your y value is positive. In the third quadrant, all your x and y values are both negative. In the fourth quadrant, all your x values are positive and all your y values are negative. Okay, and let me just fill out the quadrant. This is 1, 0, 0, 1, negative 1, 0, 0. Now, when we get to the trig test, students have asked, can you guys be given a blank unit circle? So I'm not going to give you a blank unit circle because on the AP exam, you're not going to be given one either, but I can give you a blank sheet where you can create your own unit circle. So just to give you a heads up on that, but we won't see trig until end of the unit. Right, let's see if we can fill out some of these, or let's see if we can do from 31 to 46. I'll do the first few with you, and then you guys can fill out the rest. So sine of pi over 6, we know sine of pi over 6, my order pair is √3 over 2 and 1/2. Sine is the y value, so sine of pi over 6 is just 1/2. Cosine of pi over 4, here's my order pair, 4 pi over 4. Cosine is the x value, so √2 over 2. Sine of 2 pi. 2 pi is the same thing as 0, so sine is the y value. Tangent of pi. Tangent, pi is over here. Tangent is y over x, sine over cosine. So 0 over -1, that's a real number. So that's going to be 0. But if I get something divided by 0, then I got to say undefined. So for instance, secant of pi over 2. I know secant is related to cosine. So let's find cosine first, and then we can flip cosine. So we know cosine of pi over 2 is x. It's just 0. Okay. Now 0, think of 0 as 0 over 1. So if I were to flip 0 over 1 to 1 over 0, then all of a sudden it becomes undefined. So undefined or does not exist. So anytime I'm flipping 0, I'm always going to force that 0 in the denominator, which is undefined. Okay, let's see if we can work up to 42, and then we can do 43 to 45 together. Sorry, two big things with trig that we need to know is unit circle and then being able to solve trig equations. So we can do some trig equations practice tomorrow. But we don't have to worry about like law of sines, law of cosines, and all the more complex rules, sum and difference. We don't have to worry about those. Right, 43 says find where sine is equal to 1/2. So sine is equal to 1/2. We're looking for where the y value is going to be a positive 1/2. So pi over 6, first quadrant. We also know that sine is positive in the second quadrant. So the variation of pi over 6 in the second quadrant is 5 pi over 6. So pi over 6 and 5 pi over 6. Where is tangent equal to 0? Tangent is y over x. Y over x is 0 over 1. So we want to find out where is there 0 over 1 that's going to show up. So here at when theta is 0, when theta is pi, and then also when theta is 2 pi. So because we're including 2 pi there. Okay, when is cosine equal to -1? We know that cosine is equal to -1 or 1 or -1 in the x values, right? X values of along my my x and y axis, my axis here. So -1 is going to be at pi, and that's it, right? At least between 0 and 2 pi. We don't have to worry too much about graphs, but just as a quick review, sine graph starts at 0 and then goes up. Cosine starts at 1 and it goes down. It's like a cup. Tangent has a positive slope to it. Cotangent has a negative slope to it. And then cosecant and secant are just kind of parabolas that's building off of the peaks and valleys of your sine and cosine graph. Okay, let's do a few of these and then we can pick up tomorrow. So let's see if we can get there maybe 4 to 6 of these problems on page 11. Okay, we're asking when is sine equal to 1/2? For what theta value does the ratio equal to 1/2? So we can go back to our unit circle. We know that 1/2 is going to be in that pi over 6 family, first and second quadrant. Cosine is going to have a ratio of -1 when x is pi. Cosine is equal to √3/2. I know that cosine is equal to 1/2 at pi over 3, so pi over 6 is going to be in that pi over 6 family, and cosine is going to be positive in the first and fourth quadrants, so pi over 6, and then the variation of pi over 6 in the fourth quadrant is going to be slightly less than double, so 11 pi over 6. We know 12 over 6 is 2 pi, so slightly less than that, 11 pi over 6. 2 sine of x is -1. If I clean this up by moving that 2 over, sine is equal to -1/2. So similar to this, we know it's going to be in that pi over 6 family, but instead of the first and second quadrant, it's going to be the third and fourth quadrant. √2/2, that's going to be in that pi over 4 family. Positive cosine is going to be, again, first and fourth quadrants. Fourth quadrant, we know it's going to be slightly less than 2 pi. So 8 over 4 is 2 pi. Slightly less than that is 7 pi over 4. Okay, last one here. Cosine of x over 2 is √3/2. If this x over 2 kind of makes things a little more complicated, what if I just get that x over 2 by itself, and I move this cosine over and make it inverse cosine of √3/2? In other words, this is basically saying, when is cosine of theta equal to √3/2? So we just treat this like a separate problem for now. When is cosine equal to √3/2? We know it's going to be, again, in that pi over 6 family. So we know it's going to be pi over 6 and 11 pi over 6. So now I'm just going to set up my equations twice to solve for x. I'm going to set this equal to pi over 6, solve for x, and then set x equals 2 equal to 11 pi over 6, and then solve for x. Two pi over 6, same thing as pi over 3. But if I tried it with this one, x over 2 equal to 11 pi over 6. I get x equals to 22 pi over 6, which is 11 pi over 3. And 11 pi over 3 is outside of my interval, so this doesn't quite fit. We can remove that, just pi over 3. Okay, so tomorrow we'll do solving trig equations, log equations, and exponential equations, and also talk about log properties. And then Friday we will do a overall review of this unit. All right, come get your phones. So let me just write it this way. This is the same thing as basically asking yourself, what x value allows cosine to be? So this is the same thing as saying x equals inverse cosine. This allows me to get that x by itself. So you would still solve it the same way. You would say, well, this is just equal to 5%, right?
Right.
You can do it without having to go to inverse. But the advantage of doing inverse is that it allows me to handle this a little bit separately. So this kind of feels complicated. So if I just treat that x over 2 as its own variable, I can kind of just move this cosine over and just solve the same way that I did here.
Okay.
So then this becomes 5 or 6, but then if I do it this way, it allows me to move to the next step and just try to solve for that.
So I just think that the circle, same way I would look at cosines.
Yeah, it's the same thing as saying, you know, what theta allows cosine. Yeah. Yeah. Oh, there you go.